Okay, so in this video, we're going to discuss the basic graphs of rational functions. So I'll be discussing things that look like this. Okay, so rational functions, just to make sure we're on the same page. So these are functions of the form, you have f of x over g of x, shouldn't equal 0. And f of x and g of x, these are both polynomials. Okay, so there's a lot you can say about rational functions, but the two most basic graphs are the functions 1 over x and 1 over x squared. So first let's just dissect what those look like. Okay, so for 1 over x, so I have a whole bunch of points here. So I've got a graph and I've got a table. So I just want to go through and evaluate all these different points just to kind of help us figure out the shape of this. So if I plug in, say, -2, I will get -1/2. If I plug in -1 into this function, 1 over -1, that will equal -1. And then if I plug in -1/2, so I'll just pull up the work for this in case you need to wrap your head around it. So 1 over -1/2, that's equal to 1 divided by -1/2. You can see that here, and then that's going to be 1 times -2, so this just equals -2. So we get the value -2. So you can pause the video if you need to look that over. Now, if I plug 0 into this function, this is important. 1 divided by 0 does not exist, so we just want to note that. And then when I get to the positive side of this function, it's the same values as before, except they're all positive. Okay, so now what I want to do, and what I think you should do, is just take a second to plot these points. So pause the video if you need to. So I'm going to go ahead and I've magically already plotted these and gotten these set up. So you can see this curvy shape that is being carved out here. And so here's what this function looks like. So it will not cross, so notice each arm, it will not cross the x or the y axis. So there's several things we can say about this function now that we've got it graphed. Okay, first and foremost, the domain and range, we always talk about those. So the domain and range is really all real numbers except for 0. So the graph will not cross the y-axis, which means it will never get to x equals 0. And the same thing can be said for the range. So the graph will also not cross the x-axis, meaning the x-axis stands for y equals 0, so the function will never equal 0. So there's the domain and range. Next, so these lines here, these are kind of important. So we say that the graph is discontinuous at x equals 0. So you find a discontinuity whenever there's a number that you can't plug in. So at 0, I have a problem. This graph does not exist. So the graph is discontinuous at x equals 0 is how we would describe that. And these invisible lines here, they're not invisible, they're the axes, but the x-axis and the y-axis are known as asymptotes, which are invisible lines that the graph cannot cross. And then the last thing just to notice to note in terms of symmetry. So if I were to plug -x into my function, I would get -1 over x. This is a property of being an odd function, so that would describe the symmetry. All right. The last thing I want to point out here as far as graphing this. So whenever you learn about a new graph, you want to kind of have a couple of points to keep in mind. So the thing I remember really is these graphs are kind of each side of the graph is like a mirror kind of over the origin, right? That's one way that you could think of it. So I can remember these points. I can remember that for 1 over x, then it's just going to be the diagonal reflection of the first graph. However you kind of commit this shape to memory is good, because then if we start translating it to the left, right, up, or down, you have a sense of how to draw that. Okay, so next let's go to 1 over x squared, and I've drawn the same table, so we'll do the same exercise. Okay, so in this case, so if I plug -2 into this function, so think about this. So 1 over -2 squared, that's going to be -2 times -2 is how that breaks down. So this becomes positive 1 over 4. So this is actually a very important distinction with this type of graph. Okay, so next, if I plug in -1, I'm just going to get 1. And then if I plug in -1/2, so the math there, this is going to be equivalent to 1 divided by, so -1/2 will come out to positive 1/4. So 1 divided by -1/4 is just going to equal then 1 times 4, which equals 4. Okay, so then 0, if I plug 0 in, once again, we get a 0 in the denominator, so this graph does not exist. And then I plug in all the other values. Okay, so now that I've got a set of points here, we can go ahead and kind of carve out the shape as you see here. and then I can draw my shape. So there is 1 over x squared. So it kind of reminds us of 1 over x, right? However, both parts of the graph are above the x-axis, and the arms are maybe just a little bit more outstretched because this is 1 over x squared. Okay, so once again, let's just discuss domain and range. So the domain is all x values. So I can really put in any x value that I want except for 0, right? We found that in the table. And the range, so there are no y values under here, right? So they actually all start just above the x-axis. So we say that range starts at 0, but 0 is not included because this graph can never touch y equals 0, and then it just keeps going up to infinity. Okay, next, just where is the graph discontinuous? So again, what values can you not plug into this function? That would be 0, so same as before. The x and the y axis still act as asymptotes in this case. And then if I were to plug in negative x into this, this becomes 1 over x squared. So if I plug in negative x, this just gets me back to the original function. So this function, the symmetry, this is an even function. So that's the type of symmetry that we have. And now in this case, so again, you just want to like try to remember where these points are to get that general shape and just kind of how everything relates. Everything's above the x-axis. However you kind of can take a mental photograph of this will help you when we start translating. Okay, so now that we've discussed the basic graphs, just translations work like they would with any other function. So what we're going to do now is we're just going to graph a couple of these using those base graphs. Okay, so I'll walk you through how I think about this. So I've got 1 over x plus 2 squared minus 2. So the first thing we're just going to think about, right, is how does this thing translate? So the minus 2 over here, what does this mean? This means that my graph is going to go down 2. This plus 1 means that we're going to go to the left 1. And this is really the graph of 1 over x squared. So it's just 1 over x squared moved down 2 and left 1. Okay, so what I'm going to do is I'm going to think about where were those points that I had before and how would they move. So if I think about the points that were in this little quadrant here, so I had 1, 1, right? So I'm going to move that to the left 1 and down 2. So let's see, actually I'll use the green color. So left 1, down 2. Okay, do you see where I plugged that first one? Then I also had 1/2 and 4. So I'm going to move that now to the left 1 and down 2. Let's see, left. So just be careful with this. So left 1, down 2. Okay, down 1, 2. Okay. So just be careful. Make sure that, so here's where your 1/2 is. So to move that over 1, you're going to move it over to here, right? And then I also had 2 and 1/4. So if I locate where that was, and then I move it down 1, or left 1 and then down 2, it's going to put me somewhere around here. Okay, so there's one arm. Now, here's a little trick for you. The asymptote, which was originally right here, this is also going to move with the function. It's going to move to the left or to the left and then down in the same way. So for the asymptote that was here, this is going to move left 1. So this is going to help us with carving out the shape. So I'm going to draw a little asymptote here. I'm just going to know internally that this stays where it's at. And then the other asymptote that went this way, this will move down 2. So I'm just going to note that for myself. So now I have the 3 like points that, you know, I just moved them, and I have the asymptotes. So I can draw a pretty darn good approximation of this. Like that. And then I can just mirror those points on the other side. So like so. So once I kind of get 3 of those points and then I know that general shape, I think you can draw a pretty good approximation. And I guess also getting those asymptotes. So it's not necessarily like super quick, because you might have to think about kind of where those points are, but you do know like how they should move. So it's a little bit of a thought exercise, but you know, it still looks like the general shape. Okay, so we have one other graph here, -2 over x plus 1. Okay, so what if like this is messing with your head? What is like a hack for this? So I would still say to try to look at the graph and maybe first just do your best to think of how everything translates. So for instance, the negative here means the graph is flipped. Let's see, flipped over the x-axis. And then the +1 means the graph moves up. And then the 2 will be a stretch factor. Okay, now if multiplying by the number messes with your head, so what I would recommend doing is first let's maybe just draw our asymptotes. So I had an asymptote here on the y-axis. This did not move left or right, right? There's no left or right movement. So I'm just going to take a moment to note the asymptote. So I'm going to go this way. Okay. And then the other asymptote moved up 1, right? So I had no left or right movement, so this asymptote stays the same, but the asymptote that goes here, that needs to move up 1. So I'm just going to go ahead and note that. Okay, so I know the general shape of this. I should have a graph here in this quadrant and then a graph here in this quadrant. So if I get a couple points here, then I can just mirror them on the other side. So if the stretch factor is like playing with your head, make a table to help you. So let me clear some space. And so I just want to know at least like the 3 points that I had over here. So how did those maybe change? So I'm still going to use the same points. Same points on that side. So let's make this 1/2, 1, and 2. So what happens if I plug these in? How does the stretch factor impact this? Okay, so if I plug 1/2 into this, so let's see, I'm going to have -2 over 1/2 plus 1. So this comes out to -2 times 2 plus 1. So that's going to equal -3. Okay, so there's the first one. Next, what happens when I plug 1 in? If I plug 1 into this, I get -2 plus 1, so that's just going to equal -1. And then if I plug 2 into this, so I'm going to have -2 over 2, so this whole thing will become -1 plus 1, so this will just equal 0. Okay, so I've got a couple points to work with now. So let's see, let's go ahead and plot those, and then let's see if I can just mirror them. So I've got 1/2, -3. Let's see, I'll use the green color just so you can see a little better. 1, -1, and then 0, 2. Okay, so this fulfills everything that we said about the graph, right? So I can see that this has been moved up. It's going to travel next to the asymptote, which moved up, but it's also flipped. So this is going to work like that. Okay, so now where should the other arm of this graph go? Does that go over here or up here? Well, this is the graph of just 1 over x, right? Except this is translated. So I can draw now the similar points in this part of the graph, and that will maintain the symmetry of the graph. So let's see. Looks like I'm going to have a point here. And then we'll have one here. And then it looks like we'll have one going up 2 more this way. So I just kind of drew an approximation of the other arm. But now I've met the conditions of this graph. Okay, so translations work the same. They might mess with your head. So if you're really worried about what points to draw, you can always still go back to the table method, though it is helpful to know about translations and to know how the graph moves. So the last question I have is, what about higher powers of n? So if I have f of x equals 1 over x to the n. Well, let's just take a quick field trip. So here we are at my favorite site, Desmos.com, just to do like a quick investigation of this. So notice I have higher powers of 1 over x, and these are all odd powers, just so that we can see how this works. And if you've been watching my series, you probably have a guess as to what's going to happen. Okay, so 1 over x to the third looks very similar to 1 over x, right? It just looks a little bit more elongated. And then what about if I go to 1 over x to the fifth? Same idea, right? It just starts to flatten out a little more. So if I just zoom in a little bit. So you can see that these graphs always meet at the point 1, 1 and negative 1, 1, or negative 1, negative 1. And then they get a little flatter as they get a higher power on this part of the graph, and then they get a little more narrow on this part of the graph. So if I continue with this, what about 1 over x to the seventh over here? Okay, 1 over x to the seventh still looks the same. What about 1 over x to the ninth? Still looks the same. So the higher powers of x, they still behave like 1 over x. They just get a little bit more like narrow in some parts and maybe like a little more flattened in other parts. So let's compare that to even powers of x. All right, so now I've got even powers of x. So for 1 over x to the fourth, looks very similar to 1 over x squared. If we look at 1 over x to the sixth, same idea. So it very much works, you know, it still maintains that shape. Again, it just gets flatter as we go to like higher powers down on this part, and then it gets more narrow on the inside. So we've seen those patterns before. They still hold here. Okay, and so that brings us to the end of this video. So that should give you just a nice overview of just the basic graphs. I have more in this series about crazier looking graphs, so I will catch you guys in another video. Thanks for watching.